If you are in any way familiar with the idea of flat Earth, you might have heard people use the expression 8 inch per mile squared to claim that certain buildings or mountains should not be visible to us, as they supposedly should have disappeared behind the horizon. Now, there are multiple things wrong with this equation, and I will show you why. After that, I will show you improvements on the equation that more accurately reflect reality. So, let's draw a circle. This is Earth, and r is the radius. Let's say we find ourselves here at the so-called top of the sphere. At some distance dA, there will be a tall object. The angle between us and the object over here is theta. Now, the equation 8 inch per mile squared describes the distance between this horizontal line and the Earth's surface in the line perpendicular to it. According to this equation, our tall object should not be visible anymore as this distance f is greater than the height of our object. But there's a problem with this equation, and it is not the fact that it describes a parabolic curve, because for not too great distances, it does very accurately describe f. The problem is that this assumes this horizontal line is our line of sight, meaning that our eye level will be on the ground, when in reality it is possibly several meters up, and in that case our line of sight will be this line. You can now see suddenly a greater section of our object is visible. So, can we derive an equation that gives us this obscure distance of the object? First, where the line of sight meets the horizon should be connected to the center of Earth. Now we have two separate angles. This is helpful because this forms two right-angled triangles, and these have very well-known geometric rules. So we want to know this obscure distance, FA, the actual drop, for a given distance from the observer. I will call it dA, the actual distance. The length of an arc, in this case dA, is given by the total angle, theta plus alpha, and multiplied by the radius, in this case the radius of Earth, where the angles are measured in radians. 2 pi times r would be the entire circumference of Earth. Now, for any right-angled triangle, the cosine of the angle is the adjacent side divided by the hypotenuse. We can do this for both triangles. Take the inverse to get the expressions for the angles and plug them back into the length of an arc. In any given situation, we will know our distance to the object, our observing altitude, and the radius of Earth. But we want to know what our obscure distance FA is. So let's rearrange this equation. This is just algebra, so put your high school math skills to work. What we end up with is this equation. So let's compare. First of all, this green dashed line is the 8 inch per mile squared equation. The pink one is the same equation basically, but it assumes a spherical and not a parabolic Earth. As you can see, it does not matter much at short distances. The blue line, however, includes an observer height of just 10 meters, and as you can see, it makes quite a difference. At around 100 kilometers, the 8 inch per mile squared equation overestimates the drop by 167 meters. But this equation is also overestimating the obscure distance, or drop, as it does not include the atmospheric refraction. Now, a lot of flat earthers will say that this is an excuse to explain away any problem regarding being able to see objects that seem too far away. The advanced Earth curvature calculator is nice, but flat earthers can always try and claim that there's some fudging of numbers going on behind the scenes. And that is why I will prove to you the effects of atmospheric refraction in an equation. This will be basically a mathematical proof, and the maths don't lie. If I can find an equation that describes reality while assuming a spherical Earth, that means that the Earth is of course spherical. Just like a prism, when a light ray changes medium, its path gets bent. Most of us will have played with prisms at some point in our lives. And imagine that the Earth has a two-layered atmosphere. At the top part, it has a lower density, and as a light ray comes in from space, it gets bent. But then it encounters the bottom layer, which is denser, and it gets bent again. The atmosphere in reality has an infinite amount of infinitely thin layers with lower density as you go up. This smooths out our light ray and gives it a nice curve. Let's define a new variable. Curvature is 1 divided by the radius of the thing that curves. The larger the radius, the lower the curvature. Makes sense. The curvature of Earth with respect to the light ray is less than if the ray was going straight. So the effective curvature is the curvature of Earth minus the curvature of the light ray. If the curvature of the ray was 0, meaning it is going in a straight line, then the curvature of Earth seems normal from the perspective of the ray. If the curvature of the ray is equal to that of Earth, that means the ray sees no curvature from its perspective as it goes around the planet, and the effective curvature is 0. If we know the effective curvature, we know the effective radius of the planet, which we can plug in our equation from before, which will result in an equation that takes refraction into account. So how do we calculate this effective curvature? Let's say we have two radio towers that are sending signals. As the signals or rays pass through the atmosphere, their wavefronts will get bent or refracted. The higher the altitude, the weaker the refraction is. Also, the wavelengths of the ray will decrease more than at the top. Wavelengths get shorter after refracting by this amount, divided by the refraction index, which is dependent on altitude. Trace out the path of the rays and you will end up with a circle. The radius of this circle is the radius of the ray, which is the quantity we want to know. To do that, we need to define another quantity, the ratio between the radius and the wavelength of the ray. Now, due to the fact that we can recognize a triangle over here, we know that the ratios of this triangle should be the same as this one. The same goes for the ratio between those increments of altitude and wavelength. So rearrange and we have an expression of the radius of the ray, but we don't know this part, which is how much altitude changes with wavelength. We can take the inverse so that it is maybe a bit more intuitive. How much wavelength changes with altitude. So we take the derivative of our altitude-dependent wavelength equation from before. To calculate this, we need to know how much the refractive index changes with altitude. This is something we can do experimentally. One such formula is Cauchy's formula. I found this equation is not quite perfect, but it fits our purposes for today. So we need to take the derivative of wavelength over altitude after having plugged in our expression for the index, which is altitude dependent, as it is pressure dependent. We have to do a little bit of calculus to arrive at the expression that we need to find the radius of the ray, so that takes a little bit of time, but we end up with this. This expression of the radius of the ray has to be plugged into our equation for the effective radius, which we can then use for our original equation. Let's assume an observer height of 10 meters. What will it look like? We have the same graph right here, but now in orange the obscured height or drop due to refraction with an effective radius of a bit more than 8,000 kilometers. You can now see that the 8" per mile squared equation overestimates the drop by close to 310 meters at a distance of 100 kilometers. The internet states that typical values for the effective radius can vary and could easily be 7,300 kilometers, for example. And in that case, the 8" per mile squared equation would overestimate drop by 255 meters, a bit less. I want you to realize that this all happens when your eye level is at just 10 meters. If you were standing at 30 meters, the overestimation of the 8" per mile squared equation would be between 350 and 410 meters at 100 kilometers distance. So I hope that this has given people a little bit more insight into the effects of refraction and our line of sight. I've put various links in the description surrounding certain phenomena and equations. I will also put a Dropbox link where you can download a PDF that talks about my approach in written form. For any flat earth debunkers or even proponents, feel free to use my equation as long as you give credit. The goal of this video was to give people a little bit more insight into refraction. This should make it clear now to people how strong these effects actually are and that they are actually present. I hope to make more sciencey and mathy videos on this channel, so subscribe if that is something you want to see.